Hello, and I'd like to prove another theorem. This one is a famous theorem that's used in other branches of mathematics, and it's called the Cauchy-Schwarz inequality. And what the statement says is that if u and v are vectors in an inner product space, then the inner product of u and v squared is less than or equal to the norm of u times the norm of v. So a couple things you want to know before going through this proof. You want to know what an inner product space is. You also want to know how to find the inner product and what the norm or the magnitude represents. We are going to use the forward-backward process to do this proof. This one is what I would call a little ingenious. And it's not easy to motivate exactly why this proof comes about. So it uses a little bit of um, you could say some imaginative mathematics. But once you see how it works, it actually ties together some very interesting areas of math. And for the most part, this proof is very algebraic. So we're just going to mainly use algebra to get to the results without anything too out there. Okay, before we get started, we have to know three properties. These are the three properties of inner product spaces. Three properties of inner product spaces, and these are all in the book. So the first one is called the linear property. And that one is the main one we're going to use in this proof, and that says that the inner product of a, some expression a u1 plus b u2 and v is equal to, we just kind of separate the a and the b into two parts. A times the inner product of u and v plus b, u1 and b plus b times the inner product of u2 and v. So in a way, it's almost like the a and b get removed or factored out. And then we have two things that are being added. And then the second property is the symmetric property. And the symmetric property says that the inner product of u and v is the same thing as the inner product of v and u. So we can switch around the two things inside the product space. And then finally, the third property is the positive definite property. And what that says is that if we have an inner product with itself, so u and u, the vectors, that is positive, greater than or equal to 0, or I should say non-negative. And the inner product of u with itself is equal to 0 only if and only if u is 0. So remember, an if and only if goes both ways. That says that if we have an inner product of a vector with itself, we get 0. That means that that vector is 0. And then going the other way, if we have a vector that's equal to 0 and we find the inner product of it with itself, that inner product must also be 0. Okay, we're going to get to the proof. And before I do that, I just want to mention that this proof uses a little bit of a different technique. Not only are we using the forwards-backwards method, we are also using something called specialization. specialization. So the way specialization works, we're going to show that this is true for all vectors u and v. And we look for an object. In this case, we're going to try to create this object down here. We're going to try to create this object and show using the forward process. So with the backward process, we're going to create the object. In this case, we have an inequality. And then using the forward process, we're going to show that we can create this object. So that's the way specialization works. Watch the video that I put in the in this assignment to see a little bit more about how that. So anytime we have the words for all, in this case it doesn't say for all, but it says we can assume it's for all vectors u and v. Okay, so let's get to the outline using the forward backward process. This is not the proof yet, but this is the outline using the forward backward process. So we start with A. What's our hypothesis? Well, we know that u and v are vectors in an inner product space. Okay, so remind yourself what that is. We can also verify that the inner product of u with itself, that is equal to the magnitude of u squared. And we'll be using that property inside of our proof. And similarly, the inner product of v with itself is equal to the magnitude or the norm of v quantity squared. Okay, so that is our hypothesis, and we'll work backwards from the conclusion. So way down here is our conclusion, and our conclusion has the statement that the inner product of u and v squared is less than or equal to the magnitude of u times the magnitude of v. So the question is, how do we get back? I'm going backwards, right? What's B1? Well, this one's not too bad. How do I show that we have on the left-hand side just a number here? How do we show that a number is less than or equal to another number? Well, we can move things around and we can show. So B1 is to show that the quantity u, v, the inner product of u and v squared, if we move this to the other side, subtract the magnitude of u times the magnitude of v, that should be less than or equal to what? Should be less than or equal to 0. If we can satisfy this inequality, then we have the same result as statement B. Okay, going backwards to B2. Before I get to this result, something minus something is less than or equal to 0. This is the part that's kind of ingenious. Ingenious, which is not something obvious. It's kind of clever. I guess a better word would be clever. I do not give myself credit for creating this proof, but it is very clever the way it's usually proven. We are going to look at the statement in B1 and think of it as, okay, we have two things being subtracted. One of them is squared minus the product of two other things. When have we ever seen something squared minus the product of two other numbers, and that could be equals to 0. In this case, it's less than or equal to 0. Well, the clever part here is we're going to use the quadratic formula this kind of looks like if we can show that b squared minus 4ac is less than or equal to 0. And in this case, we would have to have b be what? The inner product of u and v. And then a, well, we don't have a 4 there. So the 4 kind of comes into play with the u and the v. But we can just say that 4ac is equal to the norm of u times the norm of v. And we can use the quadratic formula. That's the inside part, right, under the square root. If we can show that's true, then with this substitution, we can prove b1. So if something can be put in this form, it has to be what's called quadratic in form, which means it has something squared plus something, right? X squared plus something x plus c equals 0. Then we can use the quadratic formula. Okay, so we're kind of stuck there. If we can show that we can turn this into a quadratic and then use the quadratic formula with this substitution over here, then b1 and b are proven. So how are we going to get back to that part? Well, if we do a, after we know a, we can go ahead and construct a inner product. And when we use that inner product, so a1, when we create this inner product, we want it to look like a quadratic. And it turns out that the term that is going to do that is if we create an inner product using the term tu plus v. So let's say t is a real number. T is a real number. And then tu plus v, comma tu plus v. If we construct that object, that's really the same thing as the magnitude or the norm of tu plus v squared. And now we're creating something that kind of looks like a quadratic. What does this kind of look like? We have it almost looks like a linear combination of u and v, except there's only something multiplying the u. That looks very similar to the linear property, and that's exactly what we're going to use. A2, we are going to use properties. In this case, the linear property, to expand that inner product in the previous step, which is the inner product of tu plus v with itself. Once we expand that product, we hope, and this will work, but only through testing this prior, we want to write the magnitude of tu plus v squared in quadratic form. In quadratic form. And the way it's going to be written is something like at squared plus bt plus c. And then the step that's going to connect it to b2 is step a4. Step 4 is that we want to take this function, or whatever it is, this expression, and we want to use the quadratic formula. Now, for the quadratic formula, the inside part of this quadratic formula, for it to be less than or equal to 0, the only way that can happen is if the quadratic equation has either complex roots or a root of 0. So we want to show show the complex, or the quadratic, it's going to have complex roots, in other words, show that the quadratic has complex roots or roots of 0. And then I'll just remind you what happens down here. We have negative b plus or minus the square root of b squared minus 4ac all over 2a. If those are our t values, the inside part here, that is less than or equal to 0 only if we have a quadratic that is above the x-axis, right? Or it has complex roots, or it could be a quadratic that just hits 0 and that's it. Okay, so here is the outline. This is the forwards-backwards process to prove the Cauchy-Schwarz inequality. The rest is really just algebra. And you'll have to probably verify some of these steps because I will go through it quickly. So pause this video if you need to verify any steps as I go through them. So first thing we're going to do is construct an inner product, tu plus v, tu plus v. Then we're going to use properties to expand that product, which will turn it into a quadratic expression, at squared plus bt plus c. And we're going to have to do some substitution. If you look over here, we have to replace b, a, and c with certain numbers. We won't know what that is until we start the proof. And then the next step is to show that this quadratic has either complex roots or roots of 0. Hence, the inside of the square root is less than or equal to 0. And then if I can do that with the following substitution, we can just plug things in and then we have the result. So let's get to it. Proof. We're going to start by constructing, so this is A1, construct the general, oh, and by the way, we have to start with A, lit U and B vectors in an inner product space. Okay, so it's very super general. A1, we're going to construct the inner product, which will have a very specific form. Why is this chosen? Because it works. And this is the magnitude of tu plus v squared, which is equal to the inner product of tu plus v, tu plus v. So I'm just showing both forms of it. We're going to start with the right-hand side. Now we're going to use step A2. By the linear property, so here's where you might have to sit down and work with that property yourself to verify this is true. We have the inner product of tu plus v with itself, tu plus v, is equal to t of the inner product of u, tu plus v, plus, and then the number in front of the v over here is a 1, so I can put a 1 out here or leave it blank, doesn't really matter, plus 1 times the inner product of v, tu plus v. Okay, we're going to use the linear property again, but before I do that, I want to switch around the order inside of these inner products. And the reason we can do that is by the symmetric property. By the symmetric property, the previous step is equal to t times the inner product of tu plus v and u plus, we can leave the 1 out there if you want, 1 times tu plus v comma v. So all I did was I switched around the two things, the vectors inside the inner product. And then from here, we're going to do more algebra by the linear property again. The previous step, okay, here's where you got to really be careful because the t is in front of the whole thing. We're going to leave a t in front here, and then remember that this underlined part is going to expand into a sum with 2 parts, so leave room for that. And using the linear property, that becomes t times the inner product u with u plus the inner product of v with u plus, and then we're going to expand this using the linear property. We get t times the inner product of u with v plus the inner product of v with v. At this point, we're going to distribute by distributing. And we're also going to use the symmetric property. Using the symmetric property, and then combining like terms. We can go ahead and multiply the t inside. We get, that's equal to t squared times the inner product of u and u, plus I'm going to switch these two around so we can combine the two uv's that we have, and the t goes in front of it, t times the inner product of u with v, plus I have another term like that, t with u and v, and then finally plus the inner product of v and v. So you should be seeing where we're headed here. This is now a quadratic formula, or a quadratic expression, I should say, not a formula, but a quadratic expression, which is equal to t squared times the inner product of u with u. T plus t is 2t plus 2t inner product u and v plus the inner product of v and v. Okay, so now that we've used the properties, we're moving on to the next part, which is A3. We are going to make some substitutions. I'm going to lit, before we put the A, B, and C in there, I'm going to lit u, the inner product of u and u, that is equal to the magnitude of u squared, because that's going to look like our final form, the B step, right? And we're also going to let VV be equal to the norm of V squared. They're really just the same thing. We just want to replace them so that way when we go ahead and solve it, we get the exact form. So we replace those. That becomes t squared times the magnitude of u squared plus 2t times the inner product of u with v plus the magnitude of v squared. Okay, so now we can see that these three pieces, they're all together in the same formula. Now we just have to use the inequality or get them into the inequality, and we're done. So let's make a substitution. This is quadratic in form. And to verify that, let's make some substitutions. Let A be equal to the magnitude of u squared. Let's let B be equal to 2 times the inner product of u and v. And then let C be equal to the magnitude of v squared. And then by substitution, this previous step becomes at squared plus bt plus c. And we know how to solve this equation. How do you solve a quadratic equation? Well, typically we would try to factor it, but we don't know exactly how to factor this. So we can use the quadratic formula. So that's A4. Now, before we do that, I want to know something about this quadratic formula. What does its shape look like? So here we're going to go back to the original. Actually, we can just look back at the previous step. So if we have the magnitude, a number squared, that's going to be positive. Same thing with C. Those are both positive. And if we add something to something that's already positive, this whole thing has to be positive. Or in this case, non-negative. I should say non-negative. And we can also verify that with the positive definite properties. Positive definite properties, we can verify that an inner product, remember an inner product with itself, UU, is greater than or equal to 0 always. And it's only equal to 0 when U is equal to 0. And same thing with V and V. And then we also know, what did we set this up as originally? This is the magnitude of TU plus V squared. We know that that's equal to AT squared plus BT plus C. So we have even more confirmation. And of course, this is bigger than 0, which means the right-hand side has to be bigger than or equal to 0. So we have a quadratic equation, and that can have one of two forms. It could be one that's above the x-axis, and that would have complex roots. That's our quadratic expression. Or we could have this be touching the x-axis, and it could have a root of 0, or roots of 0. Could be a repeated root. Either way, we know something about the quadratic formula from here. We know that the quadratic formula is not going to have any roots other than 0. It won't have any real roots other than 0. So by the quadratic formula, this is now A4, step A4. By the quadratic formula, t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. We must have the case, I remember that is called something, the number under the square root is called the discriminant, this thing right here. We must have the case that the discriminant, b squared minus 4ac, is less than or equal to 0. And now we get to B2. We're going to plug back in the A, the B, and the C. So if you forgot, I will remind you, A is the magnitude of U squared. B is the product 2 times the inner product of U and V. And then C is the magnitude of V squared. Let's plug those into this formula. by substitution. The magnitude of b squared is 2 times the inner product of u with v, quantity squared, that's b, right? Minus 4, a is the magnitude of u squared, times c, which is the magnitude of, not c, magnitude of v squared, and that is less than or equal to 0. So now you should see it. We're getting to b1. If we square the left-hand side, we get this extra 4 there, but it doesn't matter. It's going to go away. 2 times 2 is 4, and then uv, the inner product of uv squared will be the inner product of uv squared minus 4 times the magnitude of u squared times the magnitude of v squared is less than or equal to 0. And then finally, if we divide both sides by 4, divide both sides by 4, what I do to one side, I do to the other, we get that the inner product of uv squared minus the magnitude of u squared times the magnitude of v squared is less than or equal to 0. And now we have a result, which is the conclusion B. Add the magnitude of u squared v squared to both sides. I told you it's a lot of algebra. And then we have the inner product of uv squared is less than or equal to the magnitude of u squared times the magnitude of v squared. And our proof is done. Thanks for watching.